Good evening, everybody. Thank you very much for coming to the Boston chapter seminar series of IEEE Photonics Society. My name is Keisuke Kojima, chair of the society. Today's talk will be physical limits on light scattering, a complement to structural inverse design. The talk will be given by Alejandro Rodriguez. Alejandro Rodriguez is an associate professor of electrical engineering and the director of the program in material science and engineering at Princeton University. His research focuses on nanophotonics, the study of light in structural media, where he is known for his contributions to computational and mathematical methods and for his work on quantum fluctuations, nonlinear optics, and the nanophotonic inverse design. He was awarded the Presidential Early Career Award for Scientists and Engineers, the National Science Foundation Early Career Award, the Society of Hispanic Professional Engineering Young Investigator Award, and the Department of Energy Frederick A. House Award in Computational Science. He has bachelor's and PhD degrees in physics from MIT and was a postdoc fellow at Harvard University. Thank you very much.
Okay, thanks for the introduction and thanks for the invitation again. As you mentioned, I'm happy to take questions as we go. As a matter of fact, I encourage you to ask questions as we go, particularly because some of the aspects I'm going to cover are pretty technical. So by all means, just ask away. So let me start by motivating precisely what do I mean by inverse design? What do I mean by electromagnetic limits? So a lot of the recent excitement in the area of photonic design, especially in the last few years, has centered around this idea of doing large-scale optimization, so machine or computer-driven design. And the idea there is, unlike traditional photonic design, where you rely on a few set of principles like index guiding, band gap confinement, material resonances, the idea of large-scale optimization, which is synonymous with inverse design, is you kind of do away with all of that sort of intuition and understanding, and instead you choose performance over aesthetics. So you try and just brute force the problem. I'll give you an example of that in just one slide. But the idea is that you want to formulate some kind of optical response as a function of structural parameters in a computational grid or a computational cell, and you're going to kind of want to follow the gradients with respect to the optimization degrees of freedoms until you find some optimal structure that, or a structure that performs a particular function. And you can see a timeline here. This is taken from a review that we wrote recently on the topic that really kind of gets at the heart of why we really got interested in this. If you see there's a progression of work in the last 10 to 20 years or so, there's been a lot of work, increasingly complex structures being studied in experiments. You can see sort of the development of this area with devices and systems ranging from incandescent emitters, splitters, multiplexers, photonic crystals. And there's been a lot of growing interest in this, particularly because there's been a lot of experimental work in the last few years. So I'll give you a few examples of some of the neat things you can do with inverse design. But let me start with a sort of 20,000 feet perspective. So the most popular kind of inverse design technique that you might find, particularly in photonics, is known as topology optimization. And the idea there is you have a computational grid. So let's think of a finite difference discretization of Maxwell's equations. And you do what's called a material relaxation. You assume that every one of these pixels, right, which are representing, the materials and the fields inside of the domain, the optimization degree of freedom is taken to be the permittivity itself, which is allowed to vary in some range. And the idea behind inverse design is that you want to maximize some objective function that depends on the field. Okay, so it depends on Maxwell's equations, and it depends on the particular distribution of dielectric inside of the computational cell. So you're maximizing a function, and similarly, you can incorporate constraints into the system. For example, inequality constraints or equality constraints, and in order to get to some kind of working or optimal system, then what you want to do is, think of a Newton-Raphson method. Want to follow the gradients of this objective function and the constraint, subject to variations in the degrees of freedom, in the optimization degrees of freedom. And though you might think, well, a given instance of the objective will depend explicitly on the structural configuration of the system. So you might think that if you want to find these derivatives with respect to different variations in the permittivity, you might have to solve Maxwell's equations many, many, many times. It turns out that you don't. For a given configuration, if you want to find out the gradients or the derivatives, how that objective function is changing with respect to small changes in the permittivity, you can do that with just a single calculation. And that's known as an adjoint method. And I'm not going to go into the technicals of it, but if you're interested, just look up adjoint methods or check out the review paper I mentioned earlier. But the key is, you follow the gradients until you find some objective that hopefully maximizes, some structure that hopefully maximizes your objective. And here's an example of the kind of structure that you can get by running this algorithm. Okay, so let me now give you a few applications of this. So particularly, this is work that we've done fairly recently. So here's an application where doing something like inverse design makes sense, okay, where it's useful. And the application here is a multi-mode cavity for second harmonic generation. So you all know, if you have a material that's nonlinear, you can have a situation, for example, if there's a chi2 nonlinearity, where you send in light at one frequency and you get light at double the frequency. That's called harmonic generation. So this is basically what's responsible behind pretty much almost every blue laser pointer out there, right? You take infrared light, you get visible light out. So if you want to enhance these interactions, so you want to lower the power requirements of these devices, again, because you need to access strong fields. So you want optical fields that live for a very long time, so high radiative quality factors, and you want a cavity, right, a system that traps light at both wavelengths, at the excitation wavelength and at the harmonic wavelength. And if you do that, you can enhance the second harmonic generation efficiency. Namely, you can increase light matter interactions, lower power requirements, get to the same level of nonlinearity with lower power. And in particular, you can show the second harmonic generation efficiency, how efficient it is for you to convert one photon, or two photons rather, into a photon at double the frequency. Scales something like this. It scales like as the quality factors of the resonances. I think you have two modes and they lived for some time. So it scales like Q1 squared, Q2, and it scales like a nonlinear figure of merit, this nonlinear overlap figure of merit, which you see here, which quantifies how strongly, this is an integral over space, so these are spatial integrals, how strongly these two modes, E2 and E1, couple to one another. Okay, so this is effectively, you can think of this as a generalization, as a selection rule, effectively. That's a generalization to what people often call quasi-phase matching, for instance, in the context of co-propagating beams or fiber second harmonic generation. But it's a generalization because it applies to any context in E&M, and in particular, we are focused on cavities here, okay? So, and then the question is, well, how do you build a cavity that has two resonances, or accepts two resonances, and where these two modes are sort of strongly interacting with one another? This figure of merit beta, by the way, just from dimensional analysis, this thing scales like 1 over, beta square scales like 1 over the volume. So the smaller the volume, the larger the second harmonic generation efficiency, which makes sense because the stronger the interactions. And similarly for the quality factors, the longer the longer the lifetime, the more time the light has to circulate inside of the resonator and interact with the nonlinearity, right, with the material. And you can see in this scatter plot here, okay, so it's not quite a scatter plot, but it's just a example of where different devices land on this landscape. So I'm in the y-axis here, I'm showing the product of the quality factors of the two resonances, and in the x-axis, this nonlinear figure of merit, right? This inverse mode volume, let's say. And so the typical approach, for decades was to use, ring resonators, very big ring resonators. So very big V means small beta, small, nonlinear interactions, and very large quality factors, because it was very easy to figure out how to come up with a doubly resonant cavity. Okay, so these are, whispering gallery modes and so forth. But as you start miniaturizing these components, it becomes harder and harder to confine light. Photonic crystals, for instance, do not very easily allow the creation of two resonances an octave apart, right? Because typically it's hard to get one band gap, let alone two band gaps that are far separated. So band gap confinement is not really a solution. And then index guiding is limited, because as I start making these ring resonators smaller, they start radiating more, the quality factor goes down very quickly. You can see that here. State of the art in 2018 was a ring resonator that's about 50 microns big. And now there are a few, smaller demonstrations, 20 micron ring resonators, but still you're limited. And the question is, if you want to make a smaller device, increase beta, the interactions, how do we do that? And there wasn't really a clear way to go about doing that intuitively. So we set out to study this using inverse design. And we found structures that blew the beta coefficients of these ring resonators completely out of the water, orders and orders of magnitude bigger nonlinearities, by virtue of the fact that you can see an example of the structure here. The structures that are discovered by inverse design have what, first of all, they look like Rorschach tests to me. They're very unintuitive, but they are small. They're wavelength scale. You can see the dimensions on this thing. Sub-wavelength in the vertical direction. They accept two modes, so they create two resonances of relatively large quality factors, thousands to tens of thousands, and they give rise to an overlap factor, a nonlinear figure of merit that's, again, about 2 to 3 orders of magnitude bigger than the state of the art. So this is quite fantastic. And if you ask me, what's the mechanism, what's going on here? What's black here is the material, white is vacuum, it's being etched down, right? This is a slab. So what's going on here? First of all, I didn't mention this, but the optimization also allows or enforces that the light coming in from this waveguide from a channel is 100% coupled to the resonance, efficiently coupled to the resonance at both of these wavelengths. Okay, so there's also a coupling requirement that is being enforced here. And if you think about what's happening in here, the kinds of structures that it's realizing, these are structures that are using some kind of hybrid confinement mechanism. So it's using photonic crystal confinement at some scale. Okay, you can see sort of concentric rings, centered around the center of the cavity, and also doing what's called multipole cancellation. It's sort of increasing the quality factor by decreasing the amount of multiples that can be radiated from the center of the cavity. So there's a number of things that are going on here, and we can get into details of what precisely are the mechanisms. But what's really surprising is that it really gives rise to a completely new class of structure, really, for doing frequency conversion. Here's another example. Yeah, go ahead.
There was one question. What is PML? Would you like to
okay. Yeah, sure. PML here, this is basically a perfectly matched layer. So this is just a boundary condition. You can think of it as a boundary condition that enforces that the light, coming out of this computational domain is perfectly absorbed, or it's just radiating. It's equivalent to open boundary conditions. So it's just a technicality about the computation, how you terminate a computational domain. Okay, so here's another example of inverse designed. So here's a structure that, so this we did in collaboration also with my experimental collaborator at University of Washington, Kai-Mei Fu. And she has these really beautiful NV centers, there's quantum defects that radiate. And she wanted an optical structure that would enhance the radiation through Purcell enhancement, Purcell factor. And these NV centers lie about 100 nanometers from the surface of a diamond substrate. So we designed a structure, a very, very compact structure, less than a micron roughly, that would enhance the radiation, the single photon emission rate from this NV center, and simultaneously increase the collection efficiency upwards. And in particular, basically, we were able to experimentally demonstrate roughly a 14-fold improvement in the radiation rate of the emitter. So that's really nice. But all of these examples really beg the question: how do you know that you cannot do better? What is the best possible achievable performance you can get? What's the largest nonlinear interaction you can get in the prior example? What is the largest Purcell enhancement you can get from a structure, compact structure like this? So we're really talking about how do you know you have an optimal device? What's the optimal performance? And the interesting question here is, typically, what do we know? We know the materials. So we have an understanding of the material response that we're working with, but you don't know the structure. So when we talk about limits, right, we're talking about what are geometry agnostic performance bounds, asymptotics, in terms of what you can do that incorporate knowledge of what the underlying materials that you're using are. So performance bounds are really neat because they can serve as targets for development. So you can think of that as a sort of top-down, top-down perspective. We know what we can do, so therefore we can then work to achieve it. And if you combine that with inverse design, with this, which is bottom-up engineering, then this combination of inverse design and having some performance asymptotics can really give you almost the entire picture of what's possible with particular device physics, right? Knowing limits also can teach you new physics, because oftentimes when you develop an asymptotic, and again, I will go into more detail about what I mean, but when you develop asymptotics, you have to have some assumptions about the physics of the problem. And these assumptions, if they can be violated, then can give you an understanding of how to make a new device, for instance. And more importantly, they basically give you an understanding of how combining materials with nanostructuring allows you to increase the performance of devices. Okay, so it helps in guiding device engineering. Okay, so why do we need limits? The reason is simple. It's, again, we have a number of applications already in photonics where clearly inverse design is leading to new kinds of structures, better performance. But we cannot tell whether these are optimal devices. And the reason is simple. Maxwell's equations are non-linearly dependent on the permittivity. So the solution of Maxwell's equations, rather, is a nonlinear function of the structural degrees of freedom. Namely, this optimization problem is non-convex, meaning there are typically, if you want to maximize an objective, there are many local maxima, and your algorithm can very easily get stuck in a local maximum. That's because, again, non-convexity doesn't help. So the idea of a performance limit or an asymptotic is that you always basically describe a bound, right? An upper bound on this objective. And one of the things we've shown recently is that there are a set of optimization methods that can be applied to this problem to estimate, right? Or to even fully find the physical limits on any kind of performance metric you might be interested in. And it turns out this problem of doing asymptotic optimization turns out to be a convex problem. So again, I'm going to explain to you exactly what I mean by this field optimization problem. So just a note, electromagnetic asymptotics, or generally the idea of looking at limits, physical limits on devices, is very, very old. If you think about black body limits, that's a kind of asymptotic, right? And in particular, in electromagnetism, I'll give you an example of some older limits back in the 2000s or so that were fairly sophisticated. But what's really interesting is that in the last few years, we've seen just a handful of groups really develop a full mathematical and rigorous theory of wave limits. And I'm going to give you the sort of the high level picture of what's involved here. So I'm going to relegate my most of the examples I'm going to talk about in the discussion to a canonical problem, okay, which is a very, very extremely common electromagnetic problem, okay? Namely, how do I, if I have a scattering problem, I have a wave incident on some device or some object, how do I maximize the scattering cross-section or the absorption cross-section? And this has many, many applications, this particular problem, to obscurance, anti-reflection coatings. There are many, many devices that rely on scattering physics. And what do I mean by an asymptotic? Well, what do we know already about scattering cross-section? So if I have a very big object, okay, so an object whose size is much bigger than the wavelength of light, where ray optics is applicable, we already know, for instance, that the scattering cross-sections, the absorption cross-sections of these large objects, large echelon mirrors and so forth, is bounded by the area of the object. Okay, so this is what we call geometrical optics. And this is related to what we know as blackbody limits. We also know that if you have very small objects like antennas or circuits, right, and nanoparticles, plasmonic nanoparticles, they can have scattering cross sections, right? The power they can radiate per unit area can be much bigger than one. So their absorption and their scattering cross sections do not scale with the area anymore. Think Rayleigh scattering, for instance. And so you can get a huge enhancement in the scattering cross-section per unit area, but we don't know really how much, or until recently we didn't know how much. So we want to understand this question. We want to understand more generally if I have some kind of, for example, if you have a wavelength scale structure with a given set of material, right, with a given susceptibility or permittivity, incorporating as much physics of what is involved in Maxwell's equations, how do we put limits on these scattering cross sections? So that is the question that we are interested in. I'll give you an example of a recent asymptotic analysis. And in particular, I call this a toy scattering problem for reasons that will become apparent. And so one approach to understanding how much scattering an object can induce, okay, is to do what's known as a modal decomposition. So you take an object, you expand the radiation or the scattering properties of the object in multiple moments, some kind of spectral expansion, and you do a sort of resonant analysis of what happens to an incident beam as it scatters from each one of the channels, right, or each one of these multipoles. And typically you can describe the resonant characteristics of an object with a few parameters, effective parameters. This is also known as couple mode theory for those of you who are sort of have an engineering background. And in particular, if you have a channel that through which energy is exchanged with a system, you can describe that exchange through the rate at which the channel is coupling energy into the system, which I call the radiative rate, and through the absorption rate. How much absorption is there, resonant absorption is there in the system. And so, folks back in 2000s or so showed that, for example, per L, right? L is the spherical multiple moment, the angular momentum. Per L, you can come up with an expression for the scattering cross-section, the per channel resonant cross-section. And in these expressions, you can see that the radiation and the absorption rate matter. In particular, one of the things you can show is that if I have a channel and I have incident light, the rate at which the light is radiating into and out of the channel, whenever that's equal to the rate at which energy is being absorbed in the system, I can get perfect absorption, right? So this is what's called rate matching. So this kind of expression tells you how to, what's physically, intuitively, what you want to do when you design a structure. You want to match the radiation and the absorption rate in the system. But it doesn't really tell you limits, right? It doesn't say, for instance, how are these parameters, the radiative and the absorption rate, how are they determined by the size of the system, by my available material? Do I have complete choice in designing these parameters? How many of these multipoles, how many of these channels do I have available to me? Surely these things depend on the size of the system and the material and so forth. And so we need something more sophisticated to come up with this. So our goal, and again, like I said, there's been a lot of sort of recent developments that have sort of converged on the current framework, which I'll talk about very soon. But just to frame the question, our goal is that we want to come up with an upper bound on sigma, the scattering cross section. And like I said, this can be generalized to many other optical problems, as I'll show you later. And I want to do that in a way that incorporates both size constraints. So I'm going to set a size for my device, like take, a spherical ball, and I'm going to assume I have a device that can live inside there and it has some susceptibility. So I know the material that I'm working with. And I want to then, regardless of the shape of the object, come up with a limit on some scattering quantity. So like I said, these kinds of scattering problems are ubiquitous. There are many problems in E&M where the scattering cross-section or something related to the scattering cross-section is effectively the fundamental quantity of interest. Light trapping, cloaking, communication, optical forces, Purcell enhancement, all of these things are effectively scattering problems, okay? So I just want to make sure that you don't get, that you understand that this problem that I'm talking about is basically just a subset. So let me give you some basics of scattering theory, okay? So just to establish language here. So let's say I have a current in space. We know that if I have a free current in space, I can figure out what the electric field due to that current is through what's known as the Green's function, right? The vacuum Green's function. So if I know the Green's function, I can basically propagate that source and I can figure out what the field is. So assume that this field, which we'll call the incident field, is incident on some object that has some susceptibility. And again, this susceptibility is a complicated function of space, right? Because we are nanostructuring a medium. And we're going to call this susceptibility, we're going to use basically Dirac notation, operator notation, and we're going to assume it's some potential, some V, right? Some potential that is scattering light. And this scattered field can be obtained, right, if we know what the induced polarization or induced currents are in this system. So the light comes in, it reflects, in the steady state, there's multiple scattering going on, and at the end, I have set up a bound polarization current inside of the object. If I know what that current is, the induced current, then also if I apply the Green's function, then I can find what the scattered field is, and the total field is just the sum of the incident and the scattered field. So the big question really is, what are these induced polarization currents? And of course, that's determined by Maxwell's equations. And in particular, and related to Maxwell's equations, by a key quantity in scattering theory, which is known as the T operator. Okay, so the T operator is given definitionally here, right? It depends on the susceptibility, it depends on the vacuum Green's function, and in particular, a combination of these things, the inverse of this operator. This was known as the T operator, and it's an operator that when it acts on an incident field, it describes precisely the induced polarization currents in the system. So you can think of it as basically inverting Maxwell's equation. So it's like a Green's function effectively, but that incorporates all of the material properties and the structural wave effects. So this T operator is an important quantity, and we use it a lot to, particularly to conceptualize the asymptotics. And the reason is that it appears, not surprisingly, right, because it's encoding information about Maxwell's equations, it appears in expressions of interest. For instance, if you have a wave, an incident wave on a system, the absorbed powers is a quadratic function of this T operator. It depends also on the susceptibility. Asim here just means the imaginary part of this operator. Okay, the imaginary part of the susceptibility enters into the loss rate, right? The absorption rate in the system. So the point is that this is extinguished power, scattered power, all of these power expressions depend on linear or quadratic functions of this T operator, okay, of Green's functions. And it turns out you can obtain quite a lot of information from this T operator. In particular, for example, the optical theorem, which you may be familiar with, is a statement about the positivity of scattering, about the positivity of some of these expressions, okay, involving the T operator. The fact that currents can't do non-negative work, always do non-negative work. So here's an example of something you can tell. And I'm not going to go through the whole argument, okay, the mathematics, but it turns out if you take one of these expressions, okay, and you assume that passivity holds, meaning these powers have to be positive, okay, you can show, and again, don't follow the derivation. I just wanted to include it in case somebody has questions at the end. But one of the things you can show is that the singular values, okay, of this T operator, of this quantity, so again, we're thinking here algebraically, the singular values of this operator have to be bounded by this expression involving the susceptibility. So no matter how the structure looks, no matter how complicated your device is, the singular values of the T operator have to be bounded by the material response of the system. And you can just show that algebraically. It turns out you can say even more sophisticated things, as I'm going to show you soon. So the big breakthrough in thinking about wave constraints and limits came in the form of what's known as Lagrange duality. Okay, so let me explain exactly what I mean. So typically, in the primal optimization problem, which we call inverse design, you are trying to maximize a function subject to some degrees of freedoms, right? The permittivity, structural variations. This objective function is typically a quadratic function of the fields. Okay, so like I said, the T operator squared or linear function of the T operator or the electromagnetic fields, for simply speaking, because things like energy and power depend quadratically on the electric field. But the fact that these electric fields, as if you look at Maxwell's equations, the solution of the electric fields involves inverting Maxwell's equations, means that this function is highly nonlinear function of the degrees of freedom of the permittivity. You're inverting this quantity, right? And that is what makes this a non-convex problem. That's why we can never say, whether we have a global maximum or not. So the idea behind using Lagrange duality to find limits is very simple, okay? And it's the following. Rather than perform an optimization with respect to the permittivity, all right, the structural degrees of freedom, you can try and simply say, I want to optimize this objective for any possible field of interest, so any T operator, okay? Without necessarily caring about where this T operator comes from, specifying the relationship between the field and the Maxwell's equations. So if I don't care about Maxwell's equations, I can just maximize this objective subject to as effectively no constraints to begin with. And this problem is convex, right? Because basically, as a function with respect to the electric field, this objective is quadratic. You have a nice convex function. And this is great. And remember, the T operators related to the induced polarizations inside of a device. So basically, you can think of these degrees of freedom as just being polarization fields. So it's great. You have a convex problem. But of course, it's kind of a useless problem, because how are Maxwell's equations, how are the wave physics at all incorporated in this problem? And it turns out one way to incorporate wave constraints is to simply incorporate them as constraints, effectively, right? Inequality constraints on an otherwise unconstrained convex problem. And so that's sort of the idea. You relax the problem. It's called a relaxation, by saying, look, to begin with, I don't care that these optimal fields, right, or polarization fields at all say anything about Maxwell's equations. And then I'm just going to introduce aspects of Maxwell's equations through, as Lagrange constraints, effectively, in the system. I'll give you an example of what that means. For instance, you can enforce that power be conserved, something like an optical theorem. And I'll give you an example of precisely what these constraints look like. So, okay, so here's an explanation that's probably a bit more technical. So we're going to do this dual optimization problem by considering the action of the T operator on the incident field, the polarization, the induced polarizations, as degrees of freedom. And like I said, these things appear all the time in objectives. For example, the absorbed power depends quadratically on this induced polarization. And I'm using here sort of Dirac notation. So this is basically an inner product or a spatial integral of the uh, field polarizations over the imaginary part of the susceptibility throughout the domain, okay, throughout the device. Now, if you ask, well, can we enforce that Maxwell's equations be exactly satisfied for this induced polarization, this optimal polarization field? Well, that would require that you have to enforce that the definition of the T operator be satisfied everywhere in space. But that's too difficult. That would be like requiring that Maxwell's equations be satisfied. That would make the problem just as complicated as the original inverse design problem. So instead, what you do is you relax this constraint and just say, look, rather than requiring that this T operator be satisfied exactly everywhere, I'm just going to basically enforce that that this quantity, effectively, this identity, is satisfied in an integrated fashion. So if you take matrix elements of this operator with respect, for instance, to the incident fields in the problem, you're spatially averaging out Maxwell's equations over the domain. And in particular, basically, if you look at this expression here, which is just integrating out this identity over the polarization degrees of freedom throughout the domain, this expression turns out to be effectively a statement of conservation of power. Okay, it may not be apparent here yet, but if you go back through these expressions of scattered and absorb power, it turns out this is precisely what this expression is stating. There's the real power conservation, in particular the imaginary part of this expression is related to real power conservation throughout the domain. Remember, we're spatially integrating out this identity, and the real part, it turns out to be related to the conservation of reactive power. Okay, so one is talking about the amount of energy, the way in which energy flows through the system. The other one, the particular reactive power, is talking about the way in which phase is transformed in the system as light scatters from a device. And so, at a very, very high level, again, what we're doing in this dual formulation is we're optimizing with respect to polarizations, and we are enforcing that these polarizations satisfy some aspect of Maxwell's equations, namely a spatially integrated a conservation principle, in particular conservation of real power, conservation of reactive power. And again, the picture is that you're specifying this identity over some kind of coarse-grained region, okay? It turns out you can do more. So, in particular, as I mentioned, if you enforce that this identity is satisfied over, and these two things are the same, okay? I'm just multiplying by another factor of T dagger here. If you enforce that this identity is satisfied over the entire domain, that corresponds to conserving real and reactive power over that domain. But you could also project this identity onto a smaller region. For instance, if I take a domain, okay, so a computational domain, and I break it down into various subregions, and I enforce that this T operator identity be satisfied in an integrated fashion, so spatially averaged over each one of these subregions, this would clearly incorporate more and more degree of reality in the optimization, further constraints in Maxwell's equation. So I have then a set of constraints of conservation of power that must be satisfied at different scales in the problem. And so this idea of incorporating potentially finer and finer local constraints, of course limited by the computational resources, because you have many different Lagrange multipliers in the problem, is interesting, because that allows you to incorporate greater and greater wave physics into the problem. And this is, the title of the talk is, limit a complement to inverse design, because this idea really strongly complements structural optimization. In particular, you can think of in this dual framework, this idea of partitioning the domain into smaller clusters, let's say, where Maxwell's equations are satisfied in a mean field way, right? When you average them out, by breaking this down into smaller and smaller subdomains, you get, it's equivalent to, in the inverse design problem, of allowing greater degrees of freedom to participate in the optimization problem. And therefore, just like inverse design gets better and better, gives you better objectives. So say you're trying to maximize some objective with greater degrees of freedom, these asymptotic, which might originally be very loose if you're just enforcing global conservation of power, right? That Maxwell's equations be just enforced on average, everywhere. As you start enforcing more and more of these cluster power conservation constraints, you get better and better asymptotics, tighter limits, and the performance gap, okay, which is what we call the gap you might have when you investigate, when you have some asymptotic, some upper bound, and you gauge it against an inverse design, a known structure. This gap presumably should go down, right? As you incorporate more and more realism, and it tells you something about the degree to which your optimization problem may be stuck, right? Your structural optimization may be far from being globally optimal. So this is kind of a neat perspective. And so we tried, we started by looking at a simple problem, like I mentioned, this scattering problem. So what are the upper bounds on the scattering cross sections for a structure, okay, that for any structure that can be effectively put inside of a spherical ball of some radius, okay? So these plots show the largest scattering cross sections you can get, so the largest power that can be scattered from a device, divided by the geometric cross section. You can think of this just by divided by the area, okay, of the physical area of the device. And on the x-axis, you see basically the radius of the spherical boundary enclosing the device. So again, these are limits. They don't say anything about what the optimal structures are. They tell you only what the optimal fields and therefore the optimal objectives that you can expect for any structure that can be designed within this spherical region, okay? And on the left, you see predictions or results for metals. So for a choice of material susceptibility, real part of chi is -10. That's basically a metal. And then a dielectric on the right with real part of chi is 16, germanium or silicon near infrared. And what you can see is, well, first of all, in these results, we are just enforcing global power conservation. So given the size of the structure, I just want the net power coming in and out to be conserved. And what's quite remarkable is how much just this simple constraint helps, okay, how accurate it is. So these lines, the different colors, are just different values of the dissipation, okay, material susceptibility, imaginary part of permittivity, okay? And what you can see is for all of these, or qualitatively, at very small devices, for very small, these are sub-wavelength devices, so it's R over lambda. The scattering cross sections end up being very small, okay? That's true for dielectrics and for metals. But for metals, you start to see that the scattering cross sections can become quite significant, a lot greater than 1. Okay, so 1 would be something like ray optics, right? Just the geometric cross section. So these absorption cross sections can be and scattering cross sections can be much, much bigger than 1, even for sub-wavelength regions, right? For a sub-wavelength device. And this makes a lot of sense because we know, for instance, metallic systems allow plasmonic resonances, right, for sub-wavelength length scales. And so these limits are already incorporating the possibility of having plasmonic enhancement, material enhancement in metallic systems. For dielectrics, if I'm going to ask you to focus just on the solid lines for now. For dielectrics, that's not true. You have to become wavelength scale. So only when you start getting to roughly R over lambda is 1, you start seeing very significant cross sections competing with the cross sections that you would get with a metal. So that's quite remarkable that just this global conservation is allowed to it gives you something so much qualitative insight. But there's more to this, actually. In addition to qualitative insight, you can see these dotted lines, both on the left and on the right. These dotted lines are the predictions of scattering cross sections you get from applying structural optimization or inverse design. So again, you're just exploring a huge number of degrees of freedom, and the kinds of structures you get are very complicated. You see some of them here. These very complicated structures for this susceptibility, of course. You can see that the predictions of inverse design are coming extremely close. So you're supposed to look at the green dots compared to the green solid line. Okay, so the solid line is the limit, and the dots are the predictions of inverse design. You can see they're coming to within a factor of 2 from the limit. So this is extremely surprising that just a simple global conservation constraint can give you something that's so close to inverse design, and basically it says you cannot do much better than this, right? So it means there's really diminishing returns in trying to further optimize these structures. This is the fundamental limit. You cannot do better than this. Similarly, I'll mention, these dashed lines. It turns out enforcing real power conservation is not enough. You have to enforce real and reactive power conservation. So both the real and the imaginary part of that identity become relevant. And not enforcing reactive power conservation, for instance, in the dielectric case, can have huge consequences. These dashed lines can be orders and orders of magnitude from the solid lines, which incorporate both real and reactive power. And the reason is very simple. Reactive power conservation is a statement really about how much the phase of the light can be altered by the medium, by the device. And we all know, this is very closely related to the ability to create resonances. So, if you have a resonance, there's a pi phase shift when you scatter from an object. And so this reactive power conservation ends up being very, very critical in resolving the ability of systems to create resonances. And not surprisingly, a dielectric can only create a resonance when the wavelength of light is roughly on the order of the device size. Okay, so this is effectively what this is stating. And again, you can see the inverse designs coming so close to the asymptotics. This is actually quite nice. So if you further fine-tune these calculations and you enforce, for instance, not only that global power be conserved over the entire device, okay, the radius of the spherical ball, but you break down the spherical ball into clusters, right, and enforce that power be conserved in each one of these, right, spatially integrated, of course, each one of these things, you get a further tightening of the bound. So you can see the dark solid lines versus the light solid lines are the predictions. Light solid are the predictions of global power conservation. Dark solids are the predictions when you break the system into bigger subregions and further enforce that Maxwell's equations be satisfied in each one of these. So you can see the utility of doing this kind of hierarchical partitioning. So I'm not going to go into too much details, but I'll say you can actually do quite a lot of semi-analytics here too. So it's well known, for instance, if you have a small nanoparticle and you have a wave, and you have sort of just a single channel for this wave to basically interact with the nanoparticle, you can do a very simple couple mode analysis similar to what I mentioned earlier with respect to channel asymptotics to show that the absorption cross section or the scattering cross section looks like a Lorentzian line shape, right? This is a resonant enhancement mechanism, and you can develop basically similar asymptotics in using our techniques, except instead of leaving these expressions of the radiative and absorption rates, these effective parameters that people typically relate to resonances, these expressions, we can derive expressions that directly depend on the material and the size of the system without regards to the particular structure or heuristic parameters. I'm not going to go into details of this expression, but they turn out to look just like a Lorentzian, but without phenomenological parameters. You can do the same thing, figure out what asymptotics are for periodic systems, for gratings, for slabs, so you don't have to marry yourself to objects that are enclosed into spherical regions. And again, you see very similar features for dielectrics and for metals. You see, for example, here we are looking at limits on the absorption cross-section of light incident on a slab in the normal direction. This is related, for instance, to thermal photovoltaic, solar cells. And you can see that as you make the thickness of the substrate, or the film, so you can think of a film of some thickness T, as you make the thickness bigger and bigger, your ability to get absorption, large absorption, increases until at some point, if your film is thick enough, you can get perfect absorption. Okay, so this is perfect absorptivity. And similarly, you can do the same thing for metals. And if you look at the metallic limits, these dotted lines again are the results of inverse design, so very complicated slabs and structures coming very, very close to the asymptotics. Okay, and you see sort of this transition from a small absorption to about 50% absorption, and then there's another sharp transition, and I can explain exactly what's going on here, into perfect absorption. And for dielectrics, you see a similar thing, except it's very strongly dependent on the periodicity of the structure. And effectively, what's happening is at some point your photonic crystal, effectively your grading, accepts leaky modes, and the ability to create leaky modes is basically strongly dependent on the material and strongly dependent on the thickness. And this is precisely being captured by the asymptotics. So this is quite neat. Let me see, how much time do I have? Maybe 10 more minutes?
That'll be fine. Please
Okay.
take your time.
Okay. So I'll give you another example of a really neat result we had recently. It involves limits, not only, so in all of these examples, you have an incident wave and you want to find out what is the maximum amount of power that can be absorbed from that wave. So here we considered angle integrated absorption. So imagine that you have an object and I have plane waves coming into the object in every direction. Okay, and I want to figure out what is the largest integrated absorption I can get. And it turns out this problem is very closely related to limits on thermal radiation, so black body limits. I'll tell you why. So first of all, it turns out you can easily write down an expression, again involving the T operators and the vacuum Green's functions, a scattering expression for the absorbed power, and in particular it's a trace expression. So on the left, this quantity phi here means absorbed power, the power absorbed by all of these waves. The trace is a trace expression. It just means you're summing over every incident wave coming into the object. Okay, so you're tracing out over all of the incident plane waves. This first term here basically is the net power that's extracted, or what's called the extinction, from each one of these waves. And the second term is the amount of power that's scattered. So I have a wave, and I know how much power, total power, is basically extracted from the wave, and I know how much power was scattered. The difference between the two is the absorbed power. However, whatever did not come out of the object was basically went into dissipation. It turns out the relationship to thermal radiation, by the way, it's fairly simple to point out. So reciprocity says, if you remember your electromagnetic reciprocity, I have a current source and a field. If I flip the role of the field and the current source, I'm supposed to get exactly the same thing. Okay, that's also known in statistical physics as detailed balance. So, and in particular, in this particular expression, when you do reciprocity, rather than considering fields coming into the object, you're considering sources inside of the object radiating fields outside. Okay, so that's where reciprocity comes in. And this trace it changes. The meaning of this expression changes. In particular, rather than absorbed power, you're looking at radiated power, because again, there are sources now inside of the object radiating out. This trace is now a trace over the location of the sources, so trace over each source inside of the object. This net extracted power turns out to be a local density of states, which if you remember your E&M, local density of states is just from Poynting's theorem, the total power radiated by the object. And this second term here, okay, which is quadratic in the T operator, is an absorbed power. So the difference between the total power that gets radiated, or that comes out of the object, minus the power that gets absorbed inside of the object, is the total radiated power. Okay, so again, a very similar analogous interpretation. Relationship to thermal radiation is very simple. It's just basically, when you're talking about thermal radiation, these sources have a particular meaning. Okay, so an object that you heat up, basically you excite sources inside of the object, and these are sort of stochastically fluctuating sources. And it turns out there's a well-known theorem known as the fluctuation dissipation theorem. You might also know, if you're an engineer, Johnson-Nyquist noise, right? That relates the temperature, okay, of your device, of your system, and the dissipation, so the thermal statistics of your fluctuations, the dissipation in the system, or the conductivity, right? If you, again, think of Johnson-Nyquist resistivity, right? Nyquist noise, to the amplitude of these fluctuations, so these sources, right? In particular, the mean field, the mean squared amplitude of these current sources, of these type of fluctuations. So if you know what the amplitude of these things are, and you know the radiated power, you can figure out also the overall thermal power. And you can just show very easily that the thermal power is given by an integral of the Planck distribution, okay, which is the thermal statistics, and the integral of the flux, right, the power radiated by all of these dipole sources, which turns out to be precisely this trace expression. So again, I figured, I know this is fairly technical. It's really nice, I find, to see these kinds of analogies presented in a way that makes sense. So hopefully makes sense. Okay, and again, to find this phi, right, you need to basically solve for the t operator. You need to solve Maxwell's equations. And if you want to find limits, right, the question is, how do we find limits? You do something like what we described earlier. I will mention sort of a neat way to approach the asymptotics in this case. So again, this trace means you're summing over different dipoles, right? You're looking at the maximum radiation achievable by each dipole within the object. So one way to approach this problem is, instead of considering each dipole separately, I can expand the Green's function, okay, the vacuum Green's function, in its singular basis. Okay, so if you can consider a singular value decomposition of the Green's function, then rather than considering this trace over individual dipoles, you're effectively tracing over like spherical harmonics. You can think of this as a change of basis. So rather than working in the localized basis of dipole radiators, I'm going to use some kind of spectral basis, a Fourier series, a spherical harmonics. And in particular, a natural basis to use to decompose this problem are the basis of singular vectors of the Green's function, which, if you have, for example, a spherical region, they're just spherical harmonics, okay? And it turns out one of the things you can show is that if you express this trace, and again, the big theme here I want to emphasize is, framing these problems in the language of algebra, algebraically, can actually help you to understand a lot, okay? And this is basically part of what helped us to develop this framework to begin with. So in particular, again, if you consider evaluating this trace expression in the natural basis of the vacuum Green's function, which again, it's a known quantity, analytically known quantity. Put a dipole in vacuum, find the total field. And the row here just are the singular values of the singular value decomposition. So these are eigenvalues effectively, because this is a positive definite operator. So these are the eigenvalues of the vacuum Green's function. One of the things you can show is that the t operator that optimizes this expression, again, just from basic algebra, can be written or must be written in the singular vector, in the singular basis. It's called a basis chained argument. And in particular, so such a t operator, right, the bound polarization currents must also be able to be written in the basis of the vacuum Green's function with some singular values. And in particular, if you assume both of these things, then you can very easily write an expression for the angle integrated emission or absorption in terms of the singular values of the vacuum Green's function and the singular values of the t operator. And the question is, well, what are the allowed singular values of the t operator if we don't enforce any constraints, right, from Maxwell's equations, for instance, on what this t operator must be? Then it's very easy to get a quantity that diverges. It's infinite. Okay, so the bounds would be, the largest absorption would be infinity, which would not make sense. So instead, if you try and enforce this, for example, real power conservation, integrated, of course, over the basis of singular vectors, it turns out, and I'm not going to go through the technical details, but that you can put a bound on the singular values of this t operator that depend on not only on the material, okay, and the material response, but also on the singular values of the vacuum Green's function. So the way to interpret these things is, this is saying the maximum polarization response I can get on each one of these channels, right, of radiation, is determined by the maximum material response. Now notice that you have chi squared divided by the imaginary part of chi. This is kind of a conductivity. The smaller the material dissipation, the larger the optical response that I can get. This makes a lot of sense, right? Think of a resonance, right? In the limit of zero dissipation, you can get effectively diverging resonant response. And then also, it depends on the radiative efficacy of the singular values of the vacuum Green's function are telling you something about how the size of the system affects the ability of the system to effectively radiate energy. So these singular values, of course, depend on the size of your domain. You know, how big of a device do you have? And so both of these things determine the maximum response that your system can have. So one of the things we did, and again, don't get too hung up on the technicalities, but we for a spherical domain, so if I have any object circumscribed by a spherical ball, a natural basis to express these singular vectors of G will be then spherical harmonics, okay? And then you can get exact expressions for the singular values of the vacuum Green's function in terms of their Bessel functions and so forth, and they depend on the size of the domain and so forth. And one of the beautiful things you can show is that this optimal angle integrated emission can be written as a sum over spherical harmonics for all of these channels, okay, of spherical radiation. In terms of quantities that, well, this looks very much like the expression I'd shown earlier for the prior channel asymptotics, right? In terms of the spherical angular momentum numbers, the wavelength of light, and these parameters, okay, which can be interpreted as radiative and absorption rates corresponding to each one of those channels, but that unlike in the prior asymptotics, they are directly determined by this material figure of merit, okay, this zeta material response parameter, and by the singular values of the vacuum Green's function, which depend on the volume. So the key here is that just like in the previous channel asymptotics, for each one of these channels, you can get perfect absorption whenever the radiated and absorption rates are equal, okay, under rate matching. But what's beautiful about these asymptotics is that they precisely tell you how big these radiated and absorption rates can be, depending on the size of the system and depending on the material of the system. And what's clear is that they cannot be arbitrary. So there are very strong constraints on what these radiation and absorption rates can be. So it's a really nice asymptotic in that, in this case, you're not getting not only what the best possible absorption rate is, but you're also getting some intuition about what's behind this setting this maximum. And so, you know, just like before, for instance, in terms of this material figure of merit, if you plot the largest absorptivity you can get for an object inside of a domain of radius r as a function of r, you see that the absorptivity increases as the radius gets bigger. This is the absorptivity, so it's the absorption per unit area, which scales linearly here, but that means it basically scales with the volume. The total absorptivity scales with the volume. And then for very large radii, as your system becomes much larger compared to the wavelength, you get to this ray optics limit where you get perfect absorptivity, you know, what I call the black body limits, right? But below this black body limit, below the geometrical optics limit, you can see you can get absorption cross sections that are much, much, much bigger than the black body formulas would indicate. And this is really neat to see that the asymptotics are capturing all of this. And you see also there are these bumps that develop along the way. So these are for different materials again. And these are basically consistent with the gradual excitation of each one of these radiation channels as they become available, as the systems get big enough for the radiation rates to be able to be big enough to accommodate the absorption rates, or for rate matching to take place. And then, just as before, I'll mention if you plot these asymptotics compared to inverse designs, which are the dots and squares and so forth, they're coming very, very close to what at least large-scale optimization suggests is the optimum And again, you can do the same thing not for spheres, but for planar objects. You know, black body limits for planar objects. One of the things you can show is that the largest absorptivity or the largest emissivity of an object is always one if it's a semi-infinite object, if it's a slab. But depending on the material, you may be able to approach that perfect absorption condition at smaller or larger thickness. So the film thickness also matters. If I have a too thin of an object, then I'm not going to be able to have perfect absorptivity. I think I'll skip some of these things. I'll just mention, you can apply the same ideas to find limits on all kinds of different objectives. For instance, not only thermal radiation, but radiative heat transfer from one object to another. So the concept of near field heat transfer, for instance, is very interesting. If I heat up an object close to another and the separation between them is smaller than the thermal wavelength, then again, geometrical optics fails, and you can get larger heat transfer than the black body limits would suppose. And we are able to derive a formula that precisely describes the largest heat transfer, depending on the susceptibility and the distance and so forth. And you can look at forces. For example, if you're familiar, Casimir limits on Casimir forces, and in particular, you can apply this framework to pretty much any kind of nanophotonic objective you might be interested in. Whether you're talking about waveguide bends or cloaking or lensing, imaging, focusing, multiplexing. Really, the sky's the limit. So here's an example of a final example of another kind of objective you might be interested in. So here's a metasurface, okay, sub-wavelength metasurface. We don't know exactly what the metasurface is. Again, we're looking at asymptotics. And the goal here is to try to figure out whether and to what degree you can focus light in a sub-wavelength region in the vicinity of the metasurface of different angles. So you have different plane waves at different angles, and I want a structure that maximizes focusing. It gives me the best focusing for all of these things, okay, all of these angles or channels simultaneously. And this plot is showing the largest field intensity you can expect in this focusing region as a function of the number of channels that are supposed to be transformed, okay, by the metasurface. And you can see that if you try to do this, of course, as the number of requirements, as the number of angles that must focus increases, the inverse designs go, the field intensity goes down, the effectiveness, right, the performance of the metasurface goes down. And here's some examples of what these metasurfaces look like, by the way, again, these are funky looking inverse structures. And you can see the degradation of the field focusing, right, of the field intensity with increasing number of channels. And you could ask, well, are we getting stuck? Is inverse design getting stuck because you have many objectives, right? You have many channels that must be, or maybe many incident fields that must be transformed. And the answer is not quite, actually. The limits show a similar trend, okay, a similar behavior, and the limits are about a factor of 2, almost less than a factor of 2 in many cases from the inverse design. So inverse design is not getting stuck. There's a fundamental limitation to how much you can focus in the near field. If you have many wavelengths, for instance, or if you have many incident fields. And I'll mention also some of this gap is due to the fact that, this line here is enforcing just global power conservation, whereas you can see these dots are enforcing local power conservation over smaller clusters, right? So greater degree of affinity of Maxwell's equations, more physics. But it's not that much of a difference. As a matter of fact, the trend follows. So this really, I'm going to conclude in just a second. It really, the culmination of a lot of these questions is really the question, right? The motivating question was, what is the performance gap here due to? So there are two possibilities. There's a possibility, so if you find the asymptotics, there's a possibility that the inverse designs are stuck in some local maximum and your asymptotics are tight, meaning that the asymptotic predictions, your upper bounds, are achievable by some structure out there. It's just not a structure that you either have had access to, right? Because you're getting stuck. Or there's a second possibility, which is the inverse designs are not getting stuck, okay, and you're getting globally optimal performance, but the limits are too coarse because you haven't incorporated enough physics. So one of the things that we showed very recently is that actually the situation at hand is this. In particular, you can prove that in the limit, as these mean field clusters, right? As you break up these domains into smaller subdomains, and you enforce Maxwell's equations over these. In the limit, as these clusters become smaller and smaller, the inverses, the asymptotics become tight. Okay, perfectly tight, meaning they can lead to a realizable structure. And so it turns out these asymptotics, this is called a strongly dual optimization problem, close the performance gap between inverse design, okay, that we saw with inverse design. And not only that, but actually this top-down dual optimization method actually doesn't give you knowledge of the best structure, it just gives you the best fields, right, the best performance. But it turns out these optimal fields can be used as a starting point for doing inverse design. So it turns out these limits can actually be useful for speeding up the convergence, right, of large-scale optimization. And so I think we're much closer to this situation than we previously thought possible. So I'll mention I'll finish by saying, related ideas are applicable to other wave problems. So any kind of wave problem where that can be framed effectively as a linear scattering problem, for example, quantum fluid mechanics, phonon, electron scattering, all of these things could benefit from the same framework, from the same formulation. So thank you very much, and happy to take questions.
Thank you very much for a very exciting talk. And now the floor is open to questions. A question from Dean. Will you explain the shape of the metal curve? Is there a leaky wave explanation similar to the dielectric curve? Does skin effect play a role?
I'm assuming you're referring to this. Are you referring to this particular example? Dean?
Dean, let me allow you to talk, Dean, if you're okay. You are on. You can. Shall I unmute?
Yes. Okay. So yes. So basically, yes. I mean, the in both examples, the ability to get large absorption rests on the ability to make resonances or to significantly, right, change the phase, right, of the incident light. And so it's just for a metal, right, you can do that with much thinner structures than you can with a dielectric. Of course, you still need to nanostructure, right? You can't just take a thin piece of metal and then assume you're going to get a perfect resonance at any wavelength you want. You have to nanostructure. But the point is that you can get these leaky resonances effectively with much smaller thickness than you can with the dielectric. And the second thing is that you can see that for dielectrics, there's a very sharp transition into this 50% absorption region, whereas for metals, that's not the case. And again, it has to do with the fact that the half wavelength condition for dielectric systems is pretty it's pretty sharp condition. So you really need to have that. Whereas for metals, the strong field response and the small localization scales that you can get in a metal allow you to sort of more smoothly vary the responsivity of the device. And so that's what's basically creating this sort of smoother asymptotic. But again, in both cases, the inverse designs are showing exactly the same kind of feature, the smoothness here, the sort of sharp transition here at the leaky mode condition. So it's kind of neat. But yeah, absolutely. It's basically leaky mode physics. Do your bounds say anything about the symmetry or lack thereof of a global? Actually, not quite, Alan. So again, the asymptotics. Let me see an example. the asymptotics, the asymptotics don't say, so for example, this structure here, the asymptotics just rely on you specifying a domain. Okay, so to the degree that the domain may or may not be symmetric, that might affect the kinds of structures that can exist within that domain. But for example, if I pick a domain like this or a spherical domain, I can come up with all kinds of different complicated structures inside that could potentially be the optimal structures corresponding to that optimal objective. So no, the bounds don't say anything about the symmetry or lack thereof for the design, although you could, for instance, as constraints, right, incorporate the assumption of symmetry. I'm sure that, for instance, that's actually an interesting question. If you enforce symmetry in the asymptotic, and you compare the result of the asymptotic to an asymptotic that does not enforce that symmetry, you could potentially say something about how important that symmetry is to the underlying objective. But frankly, in my experience, because electromagnetics, any wave equation effectively relies on interference effect, right? There is no unique structure. In my experience, I think it makes a lot of intuitive sense. There aren't really unique structures that perform better than all other structures. I think you can imagine a situation where you have an optimal structure and then you change some small variation on the dielectric at some point, and you change the dielectric at another point, and you get the same interference effect. So symmetry often, I think, is not quite as important in terms of getting the maximizing an objective. In so much as it's a useful tool we use to intuit the behavior of systems. The symmetry just makes it easier for us to understand what's going on, but I don't think it's fundamentally required.
Okay.
For many effects. Okay, there are some effects that of course rely on symmetry.
Is there any more questions? I have one. Let's assume we have we like to design a wavelength splitter. So you have one input and two output ports of micron square or something like that. Then
so something like this. Let me just something like this.
yes. So okay. And then you want above 1500 nanometer, you want all the power go to port 1, and the below port 2 or something like that. Can you also set the, okay.
Yeah, I was gonna show, I'm sure you're familiar with this structure here. So, Jelena Vukovic at Stanford has been doing a lot of work on these multiplexers.
Yes.
And here's such a device, right? Like this splits green, red, and blue light into different ports over a wavelength size region. I think it's maybe 2 or 3 wavelengths.
So you can calculate the upper bound for that?
Yes. As a matter of fact, we've done that. We haven't published it yet. So we're preparing a paper that shows precisely what the limits are for this kind of multiplexing setup. Of course, it depends on the size of the. You can think of this as an on-chip lens, right? Like a prism, effectively. And so it depends, of course, on the size of the domain, and it depends on the dielectric, the permittivity, and of course there's very, very strong constraints on the number of ports or channels that you can multiplex, which is you see something like what I showed here. It's actually quite constrained. You see something like this, a very, very sharp degradation of the possible performance.
I see.
And so it's really, I think it's really good to see, right, that we know there are many fundamental limitations associated with Maxwell's. Speed of light is one of them, right? Group velocity. We have all these limits, right, on what you can do, black body limits and so forth. It's really nice to see that there's at least a way to get at these things for sub-wavelength or wavelength scale domains, and that they exist, that there are very strong physical limitations.
Very good. Thank you very much.
So there's another Oh, can you provide a physical argument about why the ideal black body limit can be exceeded? Yes. Yes. I mean, see if I, yeah, here. So the idea is the following, okay? So the only reason, black body limits, scale like this, the surface area of the object is that in this ray optics regime, right? The number of rays that can interact with my device really depends on the surface area of my device. So the reason why the scattering cross sections per unit area can be a lot bigger is that if you think about a device that's on the order of the wavelength, the surface area really is not the most relevant quantity dictating that interaction strength. It's really the ability of the light to resonantly couple to the device in the first place, and that just depends on wave optics and the polarization and so forth. Now, here's what's bothering you, or what may be bothering you, and why it may not be a problem really, which is this doesn't mean that you get more radiation out of an object that's smaller. Okay, it's the radiation per unit area that is bigger. It's not the total radiation that is bigger. So as I make an object bigger and bigger, the amount of radiation or as I make a device bigger and bigger, the amount of radiation I can get out of the device increases. Okay, it's monotonic. Of course, you may have to reshape the object, nanostructure. The limits just tell you what the maximum is. As I change the size of the device, I have to change the structure, right, to be able to achieve that limit. So it doesn't mean that that by operating here, right, at a very sub-wavelength device, I'm going to get more power than if I operate with a larger device. That's not true. A larger device will give me more power, but this smaller device will give me more power per unit area. Of course, what the limits show is that if you go too small for a particular material, you're not going to do so well, right? That there's an optimum, but it's not, I would say, the physics of absorption, okay, which is effectively the physics of radiation, of emission, are very different when you talk about wavelength scale systems compared to, geometric optics. The area of the object is not relevant. There's wave physics like interference and resonant effects that are much more relevant than just the fact that I can get more rays into a device. So anyway, that's probably the simplest explanation I can come up with. But Dean, like the key here is like a lot of people get confused by this and assume that this means that a subwavelength object is a better absorber. That's not true. It's a better absorber per unit area. So we have a few more. I'm happy to answer. Have there been applications to plasmonic field enhancement with metallic nanostructures? Would there be a maximum localized field enhancement? Yes, of course. As a matter of fact, the reason for this, this sort of where is it? This performance, right? The fact that this absorption and scattering cross sections can be much bigger for metal, even at some wavelength sizes, is really has to do with field enhancement. The larger the field is enhanced, or per cell enhancement, right? The more absorption there's going to be, right? More power concentrated in the region there's going to be. So there's definitely a lot of applications to nanoplasmonic. I mean, people work on plasmonic absorbers and plasmonic devices, and there are many different designs, right? Different kinds of designs and design principles associated with these. The question we are addressing, of course, is, what is the best you can do, and then it's the job of inverse design, let's say, to try and get to this limit. Okay, Thaddeus is asking whether there's an ability to use tools to do some tuning of scattering from the spiky spherical structures of the COVID-19. That's an interesting question. To the degree that you may be able to design a virus, the shape of a virus to do spectroscopy or so forth. I couldn't tell you. I couldn't tell you whether that's feasible or even sensible. But I will say, something. Most of these viruses, most of these biological systems have very low index. So the index contrast is not very good. So the scattering cross sections are pretty small. They're pretty terrible. So what I do know is that there are people working on things like near field spectroscopy to try to enhance the scattering cross section. So bringing a probe near the structure, um, coating these systems, or like having nearby fluorescent particles that have larger scattering cross sections, and sure, there are people who work on sort of creating plasmonic systems that can do that near, in the vicinity of microbes and bacteria and so forth. It's not my area of expertise, but I do know that it exists. Yeah, so Plamen is asking, can you elaborate on the levitation limit in the Casimir-Polder case? Yes, thank you for asking. So it turns out, and my group, we are very interested in issues related to quantum and thermal fluctuations, hence sort of the example of thermal radiation I gave earlier. So aside from sort of transferring energy, if you heat up an object can also transfer momentum, right? Radiation, these radiative waves can transfer momentum, and if I put an object in the vicinity of another object, then they exchange momentum, and so there's a force between them. And this force persists all the way down to zero temperature. And in that case, basically the origin of the force is quantum mechanical. So it's known as a Casimir force. So we were able to put a bound. So for a long time, people had tried to figure out how to design surfaces. And for example, if you think of a particle above a substrate, how to design the substrate and or the particle to try to make a Casimir force, right? A quantum fluctuation force that is repulsive. So it would allow you, for instance, to levitate an object. And we did a lot of work on this. I did a lot of work on this when I was a grad student, and we came up with a shape. But it turned out the shape, it turns out to be just basically a slab with a hole. If you have a slab with a hole and you put a sort of needle-like particle on top, it'll experience a repulsive force. Very simple idea. But the force is very small, actually, because you need the hole to be big, and that means you dilute the material. And so, we were interested to see if you could apply limits to see whether there were other structures out there that potentially could give rise to larger repulsive forces. And it turns out the limits suggest that you can, that sort of the structure we had found was about 2 orders of magnitude off from the optimum. I have reason to suspect that in this case, we're applying only these global limits. And as a matter of fact, we weren't even applying the reactive constraint, which you heard me mention multiple times during the talk. So I feel like that was too much. Those results are too rosy. But I do think that there's some room for improvement still. We're actually working on modifying these limits to make them tighter. And there's still about a factor of 10 room for improvement. But we don't know yet what the structures are. So, we're applying inverse design, for instance, to do it. It's a complicated problem because all of these fluctuation problems end up requiring, many, many scattering calculations. You have many dipoles, for instance, right? Hence these trace expressions. And so that makes them computationally challenging, and also, easy for the optimization to get stuck in local optima. But it is an interesting question we're still working on. Okay, and I have one more question, the last question. Do I understand correctly that all of the materials are nano-engineered? Oh yeah. So surely, if you think about if you think about this objective, maximizing field intensity here, the limits don't say anything about what kind of structure needs to live inside of this domain in order for you to get this result, right? It just says no matter what the structure looks like inside of this domain, this is the maximum you can get. You can see that in order to get anywhere close to this, 0 is all the way here, right? Like it's very, if you take just a slab and you ask a slab to do this kind of focusing, you get 0 basically. It doesn't do any focusing. So you need some fairly complicated nanostructures to be able to do something like this. The limits don't say anything about that, about what the structure looks like, but they're definitely limits. And the same is true in all of the examples I showed here. Okay, so you can see these kinds of structures you need in order to get perfect absorption. Fairly complicated. These kind of nanoparticles with holes and so forth. So yeah, you definitely need nanostructuring to get anywhere close to a lot of these asymptotics.
Excuse me. This Bill raised a hand. Bill,
I have a question. Can you
Yes.
hear me?
Yes.
I have a question about applying inverse design a little beyond the examples you gave of scattering and wave phenomena in electromagnetic theory. Unfortunately, the question is going a little outside of photonics. In general relativity, the metric of space is found by solving Einstein's field equations. In particular, in high dimensions, this is an extremely complicated problem. So do you have any knowledge or idea if you could apply some of these methods of inverse design to probably not calculate the optimum metrics of space, but to get reasonable, practical approximations of some different metrics with much, much less work than solving the complete Einstein field equations?
Yeah, absolutely. I mean, I can't think of a reason. I mean, it's a linear wave theory, right? So I can't think of a reason. It's just it's a linear wave theory with many more dimensions, right? But the point is that I can't think of a reason why you couldn't. I know for a fact there's lots of people working on like computational GR that spend a great deal of time in making better solvers and sort of I know there's a lot of adaptive meshing and things that are needed. So I think I can only think the bottleneck for doing these kinds of calculations would be the ability to do fast, have fast iterative solvers effectively. I know the state of the art in E&M, it's actually not that great. But we have iterative solvers that can solve 3D problems that are 2 wavelengths by 2 wavelengths by 2 wavelengths fairly easily. It's still you still need hundreds of CPUs, thousands of CPU hours to compute even a single optimization. I can imagine that with GR the situation is going to be even more challenging. Now, the neat thing about the asymptotics is that, again, you don't have to solve the full problem, right? So you do this relaxation where you're just doing field optimizations, and then you incorporate coarser and coarser descriptions of the wave equation. So because of that, there might be an advantage. Like if you're only interested in sort of, again, loose asymptotics that capture coarser gravitational physics, then you might be able to use something like this to get at the problem, without having to throw the kitchen sink at it, right? Without having to do the full computational GR calculation. And so there might be an advantage of doing that. In the case of E&M, for instance, just doing global power conservation it seems to be quite good, right? Like especially in the context of scattering, for instance. So there might be something similar you can do with GR. And absolutely, I would think in the case of GR, I guess the degrees of freedoms would be the mass distribution and so forth, but slightly different optimization parameters. But the point is, I could see that being useful. Yeah, absolutely. I'm not familiar. I'm not in that field, but I would imagine that there's got to be somebody thinking about this. Well, you're thinking about it.
Thank you.
Yeah, no problem.
Okay, thank you very much. we had lots of good questions, and it was a very exciting, very interesting talk. Thank you very much.
Thank you. Thank you. Yeah, it was very
So,
nice. Thanks
yes.
to everybody for asking questions and for the invitation. And if anybody wants to, have as questions after the fact, my email is very simple. It's arod@princeton.edu.
As I mentioned, this recording will be posted relatively soon. And this seminar series, we will have a summer vacation, and we will restart in September. So we will see you then. Thank you very much.
Okay, bye-bye.
Goodbye.
Thanks.